This presentation develops the global characterization of graphs, a theorem asserting that three conditions on an immersed submanifold S of a product M cross N are mutually equivalent. The first condition is that S is the graph of a smooth map from M to N. The second is that the restriction of the first projection to S is a diffeomorphism onto M. The third is that S meets every vertical fiber P cross N, transversely in exactly one point, where transversality means the tangent space of S and the tangent space of the fiber together span the full ambient tangent space. The central question of this theorem already appears in an elementary example. Given a curve S in the plane R2, when is S the graph of a smooth function from R to R? S is such a graph exactly when every vertical line, every set of the form P cross R for a fixed first coordinate P, meets S in precisely one point. The global characterization of graphs is the coordinate-free global version of exactly this criterion, valid for arbitrary smooth manifolds M and N in place of R. Next, two examples, a parabola, which is a graph, and a circle, which is not. On the left, a parabola is the graph of a smooth function. Every vertical fiber, the dashed vertical line, meets the parabola in exactly one point. The projection to M, the horizontal axis, sends that unique point to its first coordinate, and this projection is bijective. On the right, a circle fails the vertical line test. The vertical fiber at an interior x value meets the circle in 2 points, so uniqueness fails and condition C is violated. The theorem adds two further equivalent formulations of this uniqueness property. The first is a diffeomorphism condition on the projection from S down to M. The second is a transversality condition on the intersection of S with each vertical fiber, phrased in terms of tangent spaces at each point of intersection. The two cases just previewed, parabola and circle, now get a dynamic treatment, with the fiber sweeping across each panel. On the left, the graph of f of x equal to 0.55x squared plus 0.25. On the right, the circle. The vertical fiber at each x, the set x cross n, sweeps across the parabola. At every position, the fiber meets the parabola in exactly one point. This is the geometric content of condition C in the graph direction. The same sweep on the circle produces two intersection points at every interior fiber, the top and bottom of the circle at each x value. The two dots are spatially separated throughout the sweep, confirming that uniqueness of intersection fails for every interior fiber. At the extremal fiber, where x equals the circle's radius, the two intersection points merge into one, but the circle still fails condition C, for a different reason. The tangent space of the circle at this rightmost point is spanned by 0 and 1, the vertical direction. The tangent space of the fiber through that point is also spanned by 0 and 1. These two tangent spaces are equal, not merely intersecting. Their sum is only the vertical line, not all of R2. Transversality fails even though the intersection count is 1. The circle therefore violates condition C by two independent mechanisms: non-unique intersection at interior fibers and tangent coincidence at the extremal fibers. Fix smooth manifolds M of dimension M and N of dimension N. Their product M cross N carries a canonical smooth manifold structure of dimension M plus N. The atlas consists of all product charts, a pair of charts, one for M and one for N, yields the chart U cross phi equipped with the coordinate map phi cross psi. The transition maps for this atlas factor as products of the individual transitions, and so their smoothness follows directly from the smoothness of each factor. The Hausdorff and second countability conditions are inherited from M and N in the product topology. The Hausdorff condition will be used below to show that the diagonal of N is a closed subset of N cross N, a key step in the properness argument. Two canonical maps come with this structure: the projection Pi sub M, which sends a pair P and Q to its first component P, and the projection Pi sub N, which retains the second component Q. Both are smooth submersions. To see why Pi sub M is a submersion, compute its differential in product coordinates. The basis vector d by dxi maps to d by dxi at P, while d by dyj maps to 0. The image of the differential therefore contains all of T sub Pm, confirming surjectivity. The argument for Pi sub n is symmetric. Condition B of the main theorem, that Pi sub m restricted to S is a diffeomorphism, requires understanding this projection precisely, which is why it is established first. A fundamental structural fact about product manifolds: the tangent space at any point P and Q of M cross N decomposes canonically as a direct sum T sub Pm plus T sub Qn. The isomorphism is the map sending a tangent vector v to the pair consisting of the push forward of v under pi sub m and the push forward of v under pi sub n. This decomposition is why transversality of S with a vertical fiber can be expressed as a spanning condition on subspaces of T sub Pm direct sum T sub Qn, the ambient tangent space factors this way, and the vertical fiber's tangent space is precisely the subspace 0 direct sum T sub Qn. The proof uses product coordinates. Choose a chart for M near P and a chart for N near Q. These yield product coordinates x1 through xm, y1 through yn on M cross N near P and Q. The differential of pi sub m in these coordinates sends d by dxi to d by dxi at P and kills d by dyj. The differential of pi sub n does the reverse. Assembling these, the map psi, which pairs the two differentials, sends the m basis vectors d by dxi to the pair eim and 0, and the n basis vectors d by dyj to 0 and ejn. This maps a basis of T sub pq of m cross n bijectively to a basis of T sub pm direct sum T sub qn, so psi is a linear isomorphism. Coordinate independence follows because the projections pi sub m and pi sub n are globally defined smooth maps. Their differentials do not depend on the choice of chart. The identification T sub pq of m cross n with T sub pm direct sum T sub qn is what allows the graph of a smooth map to be treated as a submanifold whose tangent space sits inside a direct sum. The direct sum decomposition just proved becomes a moving picture. T sub pm horizontal, T sub qn vertical, base point P and Q at the origin. Let V sweep through every direction at P and Q. At each instant, the horizontal component dpi sub m of V is the push forward of V under pi sub m, and the vertical component dpi sub n of V is the push forward under pi sub n. The parallelogram closes at every angle. The decomposition of V into its two projections holds not for one vector, but across the entire tangent space at once. A purely vertical vector W, one with no m component, has dpi sub m of W equal to 0. This is the kernel of dpi sub m. The subspace of tangent vectors that project to 0 under pi sub m is exactly the vertical subspace 0 direct sum T sub Qn. These are the vectors tangent to the fiber P cross N at P and Q. The sweep is the isomorphism seen whole. At every angle, V splits uniquely into dp sub m of V and dp sub n of V, and the vertical subspace, shown here, the kernel of dp sub m, is the tangent space of the fiber P cross N, the fact the transversality argument uses next. Given an open subset U of M and a smooth map F from U to N, the graph of F is the subset of the product M cross N consisting of all pairs X and F of X as X ranges over U. When U equals all of M, this is called the global graph of F. The main theorem will assert, among other things, that S is such a global graph. Before that can be stated precisely, the graph must be shown to carry the structure of a smooth submanifold. Otherwise, the condition S equals the graph would not be a condition about submanifolds at all. The graph of any smooth map F is an embedded submanifold of M cross N of the same dimension as the domain U, namely M. The key object is the graph embedding iota sub F, which maps a point X in U to the pair X and F of X in M cross N. This map is smooth because both component functions, the identity on U and the map F, are smooth, and smoothness into a product manifold is equivalent to smoothness of each component separately. The proof has two parts. First, iota sub f is an immersion. Since P sub m composed with iota sub f equals the identity on U, the chain rule gives that the differential of P sub m composed with the differential of iota sub f equals the identity on the tangent space. An identity on the left means the differential of iota sub f is injective at every point x. Second, iota sub f is a homeomorphism onto its image. The restriction of pi sub m to the graph serves as a continuous two-sided inverse. Applying pi sub m to the pair x and f of x recovers x, and feeding x into iota sub f yields the pair x and f of x again. A smooth immersion that is simultaneously a topological embedding is a smooth embedding. This is the embedding criterion. An injective immersion that is also a homeomorphism onto its image is a smooth embedding. So the graph is an embedded submanifold of dimension m. When f is defined on all of m rather than on an open subset, the embedding iota sub f is additionally proper, a stronger conclusion that the next slide establishes. M is the domain manifold, M cross N is the product, a strictly larger space. The graph embedding iota sub f maps M into M cross N, two distinct spaces, not one space with a curve drawn in it. A point x in M travels under iota sub f to the pair x and f of x over in the product. Pi sub m carries the image point back, pi sub m of x and f of x equals x. The round trip from x to x and f of x and back is the identity on M, the left inverse identity from the previous proof, now visible as a closed spatial loop. A second point x prime runs its own loop, returning to x prime. The two loops never mix, that separation is injectivity, equal images would project to equal starting points. When f is defined on all of M, not merely on an open subset, its graph is embedded, and additionally properly embedded, which in particular forces the graph to be a closed subset of M cross N. A smooth embedding is proper when the embedding map iota sub f is a proper map. For every compact subset, K of M cross N, the preimage of K under iota sub f is compact in M. Properness has a consequence beyond topology. Properly embedded submanifolds are closed, and closed submanifolds are the natural setting for the transversality arguments in the main proof. Closeness follows from a diagonal argument. Define the map phi from M cross N to N cross N by sending x and y to the pair f of x and y. A point x and y lies in the graph of f if and only if f of x equals y, and f of x equals y holds if and only if phi of x and y lies in the diagonal delta n, the set of all pairs y and y in N cross N. Since N is Hausdorff, the diagonal delta n is closed in N cross N. The Hausdorff condition means any two distinct points of N can be separated by disjoint open sets. This implies that the complement of the diagonal is open for any pair y and y prime with y not equal to y prime. Separating open sets for y and y prime give an open neighborhood of y and y prime disjoint from the diagonal. Since phi is continuous and delta n is closed, the graph, equal to the preimage of delta n under phi, is closed. Properness means that for every compact subset K of M cross N, the preimage of K under iota sub f is compact. The preimage consists of all x in M for which the pair x and f of x lies in K. Equivalently, the image of K intersected with the graph under the projection pi sub M. Because the graph is closed and K is compact, their intersection is a closed subset of the compact set K, hence compact. The projection pi sub M is continuous, so it carries compact sets to compact sets, and the preimage iota sub f inverse of K is therefore compact. This confirms that iota sub f is a proper smooth embedding, making the graph a properly embedded, and in particular closed, submanifold of M cross N. Transversality, the next topic, requires understanding when two submanifolds of M cross N meet in a manner that controls both their intersection and their tangent spaces. The strategy for proving the graph is closed uses a map into a second product space. The left panel represents M cross N, the ambient space containing the graph. The right panel represents N cross N with the diagonal delta sub N, the set of pairs y and y, drawn as the 45-degree line. The map phi sends x and y to the pair f of x and y in N cross N. A point x and y in M cross N with y equal to f of x, that is, a point on the graph, maps under phi to f of x and y. Since y equals f of x, the pair f of x and y is the pair f of x and f of x, which lies on the diagonal. Membership in the graph is equivalent to landing on the diagonal under phi. A point x and y prime with y prime not equal to f of x, a point off the graph, maps to f of x and y prime. Since y prime is not equal to f of x, this pair is not on the diagonal. The two components are distinct, placing the image strictly off the diagonal in n cross n. The two circles are exactly the disjoint Hausdorff neighborhoods, separating that off-diagonal point from the diagonal, the picture behind why every off-diagonal point has room around it, making the complement of delta sub n open and delta sub n itself closed. Since phi is continuous, the graph, its pre-image, inherits closedness in m cross n. Transversality captures the condition that two submanifolds meet as cleanly as possible. Two submanifolds S and S' inside a manifold M intersect transversely at a point P in their intersection when one condition holds. The tangent space of S at P and the tangent space of S' at P must together span the full ambient tangent space T sub Pm. In R2, two curves cross transversely at a point when their tangent lines at that point are distinct, not parallel, not coincident. If the two curves share a tangent line at the crossing, the intersection is non-transverse, and that configuration can be destroyed by an arbitrarily small perturbation of either curve. The perturbed curve will generically have a different tangent direction, restoring transversality. Transverse intersections, by contrast, persist under small deformations. The spanning condition is an open condition in the space of smooth maps. The formal definition has two related forms. First, a smooth map F from a manifold P to M is transverse to an embedded submanifold S of M if the spanning condition below holds at every point x in the pre-image of S under F. The differential df sub x has image equal to the image of the tangent space of P under df. This image, together with the tangent space of S at f of x, must together span all of T sub f of x of M. Second, two embedded submanifolds S and S' of M intersect transversely if, at every point P in their intersection, the span of T sub Ps and T sub Ps' is all of T sub Pm. The second form is the special case of the first obtained by taking F to be the inclusion of S' into M, then the image of the differential of the inclusion at P is exactly T sub Ps', recovering the second definition. Two remarks are essential. First, every smooth submersion is transverse to every embedded submanifold. Surjectivity of the differential already fills all of the ambient tangent space, so the spanning condition holds automatically without any information about S. Second, if the pre-image of S under F is empty, the transversality condition holds vacuously. There are no points at which to check the spanning condition. This vacuous case matters in the main theorem, where condition 3 requires not only that the intersection be transverse, but that it consist of exactly one point, so an empty intersection violates that condition even though it is vacuously transverse. The transversality theorem makes the spanning condition a hypothesis that controls the regularity of preimages, which is the next result. Two curves S and S' in the plane meet at a point P. They cross with distinct slopes, which will be shown to mean they intersect transversely. The two tangent lines at P are distinct, and two distinct lines through a point span the plane. The shaded fans between them sweep out everything. T sub Ps plus T sub Ps' equals T sub Pm, transversality holds. Perturbing S' slightly changes its tangent direction, but the two tangent lines remain distinct, so the spanning persists. This is the stability of transversality seen in motion. A parabola S and the horizontal line S' meeting at the origin provide a non-transverse example. The tangent to the parabola at the origin is horizontal. The derivative of 0.4x squared at x equals 0 is 0. The tangent to the horizontal line is also horizontal. Both tangent lines are the same line. Their sum spans only the horizontal line, a one-dimensional subspace, not the full plane. The shading covers only a line, not a region. T sub Ps plus T sub Ps' is strictly smaller than T sub Pm, so transversality fails. A small tilt of S' away from horizontal immediately restores transversality. The tangent lines are again distinct, and their span fills the plane. Non-transverse crossings are the unstable, fragile configuration, the opposite behavior of the transverse case seen a moment ago. The transversality theorem has two parts, both needed in the main proof. Part A, suppose a smooth map F from P to M is transverse to an embedded submanifold S of codimension K. Then the preimage of S under F is itself an embedded submanifold of P of the same codimension K, or is the empty set. Part B, if two embedded submanifolds S and S' of M intersect transversely, their intersection is an embedded submanifold, and its codimension in M is the sum of the individual codimensions. Part B follows from Part A. Take F to be the smooth inclusion of S' into M. The inclusion is transverse to S by hypothesis. The spanning condition on tangent spaces in Part B is exactly the definition of the inclusion being transverse to S. The preimage of S under this inclusion is S intersected with S'. Applying Part A, this intersection is an embedded submanifold of S' of codimension equal to the codimension of S in M. Since S' itself has codimension equal to the codimension of S' in M, the intersection has codimension in M equal to the sum of both codimensions. The proof of Part A uses local defining functions. The local slice criterion asserts that an embedded submanifold of codimension K can be locally described as the zero set of a smooth map to Rk, whose differential is surjective at every point of the zero set. Near any point y0 in S, this supplies an open set W in M and a smooth map phi from W to Rk. S intersected with W is exactly the preimage of 0 under phi, and the differential of phi is surjective at every point of that preimage. The goal is to show that 0 is also a regular value of the composition psi equal to phi composed with F. Fix a point x in the preimage of S under F, and let Z be any element of Rk. Surjectivity of d phi at f of x gives a tangent vector u in T sub f of x of M with d phi of u equal to Z. Transversality of f with S at x decomposes u as a sum us plus df sub x of v, where us lies in T sub f of x of S and v lies in T sub x of p. Since phi vanishes identically on S, its differential kills the tangent space of S at every point, so d phi of us equals 0. Applying d phi to the decomposition, d psi sub x of v equals d phi of df sub x of v equals d phi of u minus d phi of us equals z minus 0 equals z. Since z was arbitrary, d psi sub x is surjective, making 0 a regular value of psi. The regular level set theorem states that the preimage of a regular value under a smooth map is an embedded submanifold of codimension equal to the dimension of the target. Applied here, psi inverse of 0, which equals f inverse of S locally, is an embedded submanifold of P of codimension K. The dimension count in the main proof will apply part B of this theorem to obtain the upper bound on the dimension of S. The main theorem characterizes, in three equivalent ways, when an immersed submanifold S of a product M cross N is the graph of a smooth map. Throughout, M and N are smooth manifolds, S is an immersed submanifold of their product, and pi sub M and pi sub N are the two projections. The theorem asserts that three conditions on S are mutually equivalent. The proof will establish all three implications: A implies B implies C, and C implies A, so that each condition can be verified from any other. Condition A is the conclusion. S is the graph of some smooth map F from M to N. Condition B is the projection criterion. The restriction of P sub M to S is a diffeomorphism onto M. This means the shadow of S onto M is a bijective smooth map with a smooth inverse. Every point of M has exactly one preimage in S, and the correspondence is smooth in both directions. Condition C is the transversality criterion. For every point P in M, the submanifold S and the vertical fiber P cross N meet transversely in exactly one point. Transversality here means one spanning condition. The fiber P cross N has tangent space equal to the subspace 0, direct sum T sub Qn of the ambient tangent space. Together with the tangent space of S at that point, it must span all of T sub Pm direct sum T sub Qn. The three are equivalent. When they hold, the smooth map F is recovered uniquely as Pi sub N composed with the inverse of Pi sub M restricted to S. The inverse of the diffeomorphism maps P to the unique point of S above P, and Pi sub N then reads off the N coordinate. The implication A implies B is the easiest, while C implies A requires the most structural input, including the inverse function theorem. The first implication runs from the graph condition to the diffeomorphism condition. Assume S is the graph of a smooth map F from M to N. The goal is to show that the restriction of pi sub M to S is a diffeomorphism onto M. Smoothness of pi sub M restricted to S, the inclusion of an embedded submanifold into the ambient manifold is always smooth, and pi sub M is smooth, so their composition is smooth. Bijectivity is immediate. Injectivity, if 2 points of the graph, x and f of x, and x prime and f of x prime, have the same first coordinate under pi sub M, then comparing first components gives x equals x prime, so the points coincide. Surjectivity, for any p in M, the point P and f of P belongs to the graph and projects to P. The set theoretic inverse of pi sub M restricted to S sends P to the pair P and f of P. Both component functions, the identity and f, are smooth, so this map is smooth as a map into M cross N. Its image lands in the embedded submanifold S, so the submanifold restriction criterion applies, a smooth map into an ambient manifold whose image lies in an embedded submanifold is itself smooth as a map into that submanifold. This gives that the inverse is smooth as a map into S itself. A bijective smooth map with a smooth inverse is a diffeomorphism, completing this implication. Condition B established, the next step is to deduce condition C from B, specifically that the diffeomorphism forces transversality at every fiber. The second implication runs from the diffeomorphism condition to the transversality condition. Write phi for the diffeomorphism pi sub M restricted to S and fix a point P and Q in S. Identify T sub PQ of M cross N with T sub PM, direct sum T sub Qn as before. Under this identification, the tangent space of the vertical fiber P cross N at P and Q is exactly the subspace 0 direct sum T sub Qn, vectors with no M component. The transversality condition to verify is that the sum of T sub PQS and this vertical subspace fills all of T sub PM, direct sum T sub Qn. Uniqueness of intersection comes immediately from bijectivity of phi. For each P in M, there is exactly one point S in S, with Pi sub M of S equal to P, equivalently, S intersects the fiber P cross N in exactly one point. Transversality requires the spanning argument. Since phi is a diffeomorphism, its differential at P and Q, which is the restriction of dP sub M to T sub PQS, is a linear isomorphism from T sub PQS to T sub PM. For any V in T sub PM, the isomorphism supplies a vector W in T sub PQS that projects to V. Write W in product coordinates as the pair V and Wn for some Wn in T sub Qn. Then the vector V and 0 decomposes as the sum of V and Wn, which lies in T sub PQS, and 0 and negative Wn, which lies in 0 direct sum T sub Qn. So every vector of the form V and 0 lies in the sum T sub PQS plus 0 direct sum T sub Qn. An arbitrary vector V and U then decomposes as V and 0 plus 0 and U, both summons lying in the same sum, confirming that the sum spans all of T sub Pm direct sum T sub Qn. This verifies transversality at every point P and Q in S. The deepest implication from condition C back to condition A requires a separate lemma showing that the differential of the projection is an isomorphism at every point, which in turn needs a dimension count. T sub Pm is horizontal, the fiber's tangent space, 0 direct sum, T sub Qn is vertical. T sub PQS is drawn as an oblique line with both M and N components. S aligns with neither factor. The goal is to show that an arbitrary vector V and 0 in T sub Pm lies in the sum T sub PQS plus the vertical subspace. The vector V and 0 is horizontal, it has M component V and N component 0. Since the differential of Pi sub M restricted to S is an isomorphism, a consequence of condition B, there exists a vector V and W sub N in T sub PQS whose horizontal projection is exactly V. This vector lies on the oblique line T sub PQS and has horizontal extent V. The dashed line shows the vertical drop from V and W sub n down to its horizontal projection. The correction term 0 and negative W sub n is purely vertical. It lies in the vertical subspace 0 direct sum T sub Qn. Adding it to V and W sub n cancels the n component. The sum is V and W sub n plus 0 and negative W sub n, which equals V and 0. So V and 0 decomposes as the sum of a vector in T sub PQS and a vector in the vertical subspace. Every vector of this form can be decomposed this way, which is the spanning argument for transversality. An arbitrary vector v and u in the full ambient space decomposes as the sum of v and 0 and 0 and u. The first summoned v and 0 was just shown to lie in T sub PQS plus the vertical subspace. The second summoned 0 and u lies in the vertical subspace directly, so every vector v and u lies in T sub PQS plus 0 direct sum T sub Qn, confirming that the sum of these two subspaces is the full ambient tangent space. Before proving the deepest implication, a foundational lemma about local diffeomorphisms is needed. A smooth map that is bijective and locally a diffeomorphism at every point is a global diffeomorphism. The hypothesis gives, for every point P in S, there is an open neighborhood on which phi restricts to a diffeomorphism. The conclusion asserts the set theoretic inverse, phi inverse, is smooth on all of M. The gap between hypothesis and conclusion is that the local smooth inverses are defined on different open sets and must be reconciled. Global bijectivity is what forces them to agree. At any point in the overlap of two such open sets, both local inverses must send a point to its unique preimage, so they agree on the overlap, and the global inverse is smooth everywhere. The proof. Since phi is bijective, its set theoretic inverse, phi inverse from M to S exists. Fix an arbitrary point Q in M and let P be its preimage. Because phi is a local diffeomorphism at P, the definition supplies an open neighborhood U of P in S such that phi restricted to U maps diffeomorphically onto its image phi of U. Local diffeomorphisms are open maps. The image of any open set on which phi restricts to a diffeomorphism is open in M because the local diffeomorphism is in particular a homeomorphism onto its image. So phi of U is an open neighborhood of Q in M, and the local inverse phi restricted to U inverse is smooth on phi of U. Global bijectivity now forces the global inverse phi inverse, restricted to phi of U, to agree with this local inverse. For any R in phi of U, there is exactly one preimage under phi, so both the global and local inverse must give the same answer. Therefore, phi inverse is smooth on the open neighborhood phi of U of Q. Since Q was arbitrary, phi inverse is smooth on all of M, making phi a diffeomorphism. With this lemma established, the dimension count that pins the dimension of S is the remaining ingredient needed to complete the implication from C to A. The map phi from S to M is smooth, bijective, and a local diffeomorphism at every point. The goal is to show phi inverse is smooth on all of M, upgrading the set theoretic inverse to a smooth one. Fix a point Q in M with preimage P in S. Because phi is a local diffeomorphism at P, the definition supplies an open neighborhood U of P in S on which phi restricts to a diffeomorphism. Local diffeomorphisms are open maps, so phi of U is an open neighborhood of Q in M. On the open set phi of U, the restriction of phi to U has a smooth inverse, the map phi restricted to U inverse from phi of U back to U. This local smooth inverse exists and is smooth on phi of U. The dashed arrow is phi inverse as a mere set theoretic map, guaranteed by bijectivity alone. It solidifies because bijectivity forces it to agree with the local smooth inverse on phi of U. Any R there has the same unique preimage whichever way it is computed, so phi inverse is genuinely smooth on this neighborhood of Q. The argument applies to every point Q in M. A second point Q prime has its own preimage, P prime, its own neighborhood U prime, and its own local smooth inverse. Phi inverse is smooth on a neighborhood of Q prime as well. Since Q was arbitrary, phi inverse is smooth at every point of M. It is smooth globally. Phi is therefore a diffeomorphism. The key lemma for the implication from condition C to condition A is stated next. If S intersects every vertical fiber transversely in exactly one point, then the differential of pi sub m restricted to S is a linear isomorphism at every point of S, and S has dimension m. The dimension conclusion is not obvious from the hypothesis. The hypothesis is about intersection counts and tangent space spanning, not directly about dimension. The argument uses the dimension formula for subspaces to get a lower bound on the dimension of S from the spanning condition, and the transversality theorem to get an upper bound from the single point intersection. Together, they pin the dimension exactly at m. The isomorphism of the differential then follows from the spanning condition plus the rank nullity theorem, and the inverse function theorem can apply. The dimension count begins with the lower bound. Denote by A the subspace T sub PQS, and by B the subspace 0 direct sum T sub Qn. Transversality asserts that A plus B equals the ambient space V equal to T sub Pm direct sum T sub Qn of dimension m plus n. The standard dimension formula for subspaces states that the dimension of the sum equals the sum of the dimensions minus the dimension of the intersection. Substituting the dimension of B equal to n and the dimension of V equal to m plus n gives m plus n equals dimension of S plus n minus the dimension of the intersection of A and B. Hence, dimension of S equals m plus dimension of the intersection, which is at least m. The upper bound uses the transversality theorem. Since S is locally embedded near P and Q, restrict to an embedded neighborhood S0 of P and Q in M cross N. The transversality of S with the fiber at P transfers to S0, and for sufficiently small S0, the intersection S0 intersected with P cross N consists of the single point P and Q. Applying the transversality theorem part B to S0 and P cross N in M cross N, the codimension of their intersection inside M cross N equals the sum of their individual codimensions. The intersection is a single point which has codimension m plus n. The codimension of the fiber cross n, which has dimension n, is m. Substituting m plus n equals the codimension of S0 plus m, so the codimension of S0 is n, giving dimension of S equal to m. Comparing with the lower bound, the intersection of T sub PQS with the vertical subspace has dimension 0. The two subspaces meet only at the origin. The isomorphism of the differential follows from the dimension count. Surjectivity, given any v in T sub Pm, the transversality equation allows writing the vector v and 0 as a sum of a vector w in T sub PQS and a vector in the vertical subspace. Then dpi sub m applied to w equals v, since dpi sub m kills the vertical component. Injectivity, T sub PQS has dimension m, the same as T sub Pm. A surjective linear map between spaces of the same finite dimension is automatically injective by rank nullity. The kernel has dimension equal to the domain dimension minus the image dimension, which is m minus m equal to 0. Hence, the differential is a linear isomorphism at every point of S. The inverse function theorem can now be applied at every point, making P sub m restricted to S a local diffeomorphism everywhere. The horizontal axis represents T sub Pm, and the vertical axis represents the vertical subspace 0 direct sum T sub Qn, the tangent space of the fiber P cross N. The oblique line represents T sub PQS, whose slope is not yet determined. The dimension count will fix it. The shaded fan is transversality made visible. T sub PQS and the vertical subspace together fill the ambient plane. Feeding their dimensions into the subspace dimension formula shown below isolates the dimension of S as m plus the dimension of the intersection, hence at least m. A priori, if the dimension of S were greater than m, the intersection of T sub PQS with the vertical subspace could be a non-zero line, shown here as the red region on the vertical axis. Whether the intersection is a line or just the origin depends on whether the dimension of S equals m exactly. For the upper bound, apply the transversality theorem's codimension formula, shown below, to S and the fiber locally. Their intersection is a single point of codimension m plus n, and the fiber has codimension m, which forces the dimension of S equal to m exactly. The tangent line tilts away from vertical. Any non-vertical slope is consistent with this. The theorem only excludes T sub PQS coinciding with the vertical subspace itself. With the dimension of S equal to m pinned, the lower bound gives that the intersection dimension is m minus m equals 0. The intersection of T sub PQS with the vertical subspace is just the origin. the intersection region collapses from a line to a single point. A linear map between spaces of the same finite dimension with trivial kernel is an isomorphism. So the differential of pi sub m restricted to S is a linear isomorphism at every point. The third and deepest implication proceeds in 4 steps. Step 1. Pi sub m restricted to S is a bijection. Surjectivity, condition C guarantees, for each p in M, the existence of exactly one point P and Q in S. In particular, such a point exists, so every P is in the image. Injectivity, if 2 points of S share the same first coordinate, both lie in S intersected with P cross N, and condition C says this intersection has exactly one element, forcing the 2 points to coincide. Step 2. Pi sub m restricted to S is a local diffeomorphism at every point. The preceding lemma established that the differential of pi sub m restricted to S is a linear isomorphism at every point P and Q of S. The map pi sub m restricted to S is smooth, being the restriction of the smooth projection to S composed with the inclusion. The inverse function theorem states that a smooth map whose differential is an isomorphism at a point is a local diffeomorphism in a neighborhood of that point. Since the differential is an isomorphism at every point of S, P sub m restricted to S is a local diffeomorphism everywhere. Step 3. Combining steps 1 and 2. Pi sub m restricted to S is a smooth bijective local diffeomorphism at every point. The lemma proved before the main proof applies. A smooth map that is both bijective and locally a diffeomorphism everywhere is a global diffeomorphism. Write phi for this diffeomorphism from S onto M. Step 4. Constructing f and verifying that S equals the graph of f. Define f from m to n by composing P sub n with the inverse of phi. This is smooth as a composition of 2 smooth maps. To verify S equals the graph of f, check inclusion in both directions. First, S is contained in the graph. For any point P and Q in S, phi of P and Q equals pi sub m of P and Q, which equals P. So the unique preimage phi inverse of P is the point P and Q itself. Then f of P equals pi sub n of phi inverse of P equals pi sub n of P and Q equals Q. So P and Q equals P and f of P, confirming it lies in the graph. Second, the graph is contained in S for each P in M. Phi inverse of P gives the unique preimage P and Q prime in S. Then f of P equals pi sub n of P and Q prime equals Q prime. So the graph point P and f of P equals P and Q prime, which lies in S. Both inclusions hold, so S equals the graph of f, completing the proof of all 3 implications. The local version of this result, where condition C holds at a single point, yields a local graph representation and is taken up next. The local characterization is a corollary of the global theorem. Fix a single point P and Q in S at which S and the fiber P cross N intersect transversely. The conclusion is only local. There exists a neighborhood U of P in M and an open neighborhood V of P and Q in S, such that V is the graph of some smooth map F from U to N. The global theorem required transversality at every point with exactly one intersection for every fiber. The local corollary needs only one transverse intersection at one specified point. The proof. Because S is an immersed submanifold, it is locally embedded. Choose a neighborhood W of P and Q in M cross N small enough that S intersected with W is an embedded submanifold S0. The tangent space of S0 at P and Q agrees with that of S, so the transversality of S with P cross N at P and Q is also the transversality of S0 with that fiber. By choosing W sufficiently small, the intersection S0 intersected with P cross N consists only of the point P and Q, a consequence of the transversality theorem, which forces this intersection to be a zero-dimensional embedded submanifold, hence discrete. The same dimension count and spanning argument from the main lemma apply to S0. The differential of pi sub m restricted to S0 at P and Q is a linear isomorphism. The inverse function theorem then supplies an open neighborhood V of P and Q inside S0, on which pi sub m restricts to a diffeomorphism onto an open neighborhood U of P in M. With this diffeomorphism in hand, apply the implication B implies A from the global theorem, with M replaced by U and S replaced by V. This gives that V is the graph of the smooth map pi sub n composed with the inverse of pi sub m restricted to V. The diagonal of Rn cross Rn, consisting of all pairs x and x, is the first example. Condition A holds because the diagonal is by definition the graph of the identity map. Condition B holds because the projection to the first factor sends x and x to x, and its smooth inverse sends x to x and x. Condition C, at any point P and P, the tangent space of the diagonal consists of vectors of the form V and V, while the tangent space of the fiber P cross Rn consists of vectors 0 and W. An arbitrary vector A and B decomposes as A and A, which is tangent to the diagonal, plus 0 and B minus A, which is tangent to the fiber. This spanning decomposition confirms transversality at every point. The horizontal axis in R2 is a second example. Every vertical fiber P cross R meets the horizontal axis in exactly one point, namely P and 0. At that point, the tangent to the horizontal line is the vector 1 and 0, and the tangent to the vertical fiber is the vector 0 and 1. Together they form a basis for R2, confirming transversality everywhere. The unique smooth map whose graph is this horizontal line is the constant function f0, identically 0. The diagonal example now appears concretely, with delta and the fiber at P equal to 0 meeting at the origin. The claim to make explicit is that their tangent spaces there span all of R2. At the base point 0 and 0, an arbitrary vector A and B in the ambient tangent space R2 must be decomposed into a component along the diagonal and a component along the vertical axis. The decomposition is explicit and constructive. The vector A and A lies along the diagonal, its two components are equal, so it is tangent to the set of pairs x and x. It has the same m component as the target vector A and B, but its n component is A instead of B. The correction term 0 and B minus A is purely vertical. It lies along the fiber 0 cross R. Adding it to A and A gives A and A plus 0 and B minus A equals A and B, the target vector. Every vector A and B in R2 decomposes this way. The diagonal and the vertical axis together span R2. This is transversality of the diagonal with every vertical fiber. The projection P sub m sends the diagonal point A and A to its first component A. Every point on the diagonal projects to a distinct point of M, and every point of M is the image of exactly one diagonal point. This confirms that pi sub m restricted to the diagonal is bijective. Condition B holds. The parabola t and t squared is a graph. Every vertical fiber meets it in exactly one point, the pair p and p squared. The tangent to the parabola at this point, computed by differentiating the parametrization t and t squared at t equals p, is the vector 1 and 2p. Transversality requires that 1 and 2p and 0 and 1 together span R2. Their determinant is 1 times 1 minus 0 times 2p, which equals 1, non-zero for every p. So the parabola meets every vertical fiber transversely and uniquely, and the unique smooth map with this graph is f of t equals t squared. The vertical axis is a failure case for condition C, and indeed is not a graph. For any p different from 0, the vertical axis, which consists entirely of pairs 0 and t, does not intersect the fiber p cross r at all. Existence of an intersection point fails for every p except 0. At p equal to 0, the intersection is the entire vertical axis, so uniqueness fails. Moreover, transversality fails at every point 0 and t0. The tangent space of the vertical axis there is spanned by 0 and 1, which is the same as the tangent space of the fiber 0 cross r. So, their sum is only 0 cross r, not all of R2. All three conditions fail, consistently with the fact that the vertical axis is not the graph of any function from R to R. The unit circle is the motivating failure case. The fiber 0 cross R meets the unit circle in 2 points, 0 and 1, and 0 and negative 1. Uniqueness of intersection fails at p equal to 0. Separately, transversality fails at the extremal points. At the point 1 and 0, the tangent to the circle is the vector 0 and 1, computed from the parametrization cosine theta and sine theta by differentiating at theta equal to 0. The tangent to the fiber 1 cross R is also spanned by 0 and 1. The sum is only the vertical line, not all of R2. The same failure occurs at negative 1 and 0 by symmetry. The circle violates condition C by both non-uniqueness of intersection and failure of transversality, and is correspondingly not the graph of any smooth function from R to R. The two failures of the unit circle just computed can now be seen directly in the picture. The first failure, the fiber at x equal to 0, passes through the circle at 0 and 1 and 0 and -1, two visibly separated dots on one fiber. Uniqueness fails. At the extremal fiber x equal to 1, the fiber meets the circle in exactly one point, 1 and 0. Uniqueness holds here, but the question is whether transversality also holds. The second failure, the tangent arrow of the circle at 1 and 0, and the tangent arrow of the fiber both point straight up. The two tangent spaces, computed on the previous slide, are drawn side by side, the same vertical line. Their sum cannot fill R2, so transversality fails here, independently of the uniqueness failure at the other fibers. Both failure modes are now visible simultaneously. The interior fiber dots are restored. Two intersection points at x equal to 0 show non-uniqueness. The coincident tangent arrows at 1 and 0 show the spanning failure. These are two independent reasons that the circle fails condition C and correspondingly fails to be the graph of any smooth map from R to R. The classical implicit function theorem provides the motivating comparison. Take a smooth map f from Rm plus n to Rn with f of x0 equal to 0. Suppose the partial Jacobian, the n by n matrix of partial derivatives of f with respect to the last n coordinates, is invertible at x0. Then the zero set of f is locally near x0, the graph of a smooth function g from Rm to Rn. Condition C of the global theorem is the coordinate-free manifold analog of this invertibility condition. Transversality of S with P cross N at P and Q is precisely the condition that the n component of the ambient tangent space at P and Q is not entirely contained within T sub PQS. In local coordinates, this corresponds exactly to the invertibility of the partial Jacobian df by dy. The local corollary, which gives a local graph representation near a single transverse intersection point, is the direct manifold theoretic analog of the classical implicit function theorem. The global theorem strengthens this to a global statement by requiring the transversality and uniqueness conditions to hold simultaneously at every fiber. A final structural observation, the theorem starts with S assumed only to be an immersed submanifold, a weaker condition than embeddedness. Yet verifying any one of the three equivalent conditions automatically upgrades S to a properly embedded submanifold. Condition C alone is enough to force the dimension of S to equal M via the dimension count in the main lemma. Once S is identified with the graph of a smooth map F, it is the image of the smooth embedding iota sub F, which was shown to be a proper smooth embedding. The initial hypothesis of immersion is therefore the minimal assumption needed to run the argument. The conclusion automatically strengthens it. The global characterization of graphs establishes a three-way equivalence. A submanifold S of M cross N is the graph of a smooth map from M to N if and only if the restriction of the first projection to S is a diffeomorphism, and that, in turn, holds if and only if S meets every vertical fiber, P cross N transversely in exactly one point. The proof combined four ingredients: the product manifold structure and its tangent space decomposition, the transversality theorem, which converts the spanning condition on tangent spaces into a regularity condition on preimages, the inverse function theorem, which upgrades the tangent space isomorphism to a local diffeomorphism, and the lemma on bijective local diffeomorphisms, which stitches local inverses into a global one. A byproduct of the argument is that any immersed submanifold satisfying these conditions is automatically promoted to a properly embedded submanifold. The local-global distinction mirrors the classical setting. The local corollary is the manifold theoretic implicit function theorem. A single transverse intersection point yields a local graph representation. The global theorem is the global upgrade, when transversality and uniqueness of intersection hold simultaneously for every vertical fiber. The local graph representations assemble into a globally defined smooth map from M to N. The passage from local to global is enabled by the global bijectivity of the projection, combined with the lemma on bijective local diffeomorphisms.